Okay, so when we're talking about Vesper theory, Vesper again stands for the valence shell electron pair repulsion theory. So again, if you didn't get that, it's valence shell electron pair repulsion theory, known as Vesper. And the way this works is because electrons are all negatively charged, if you remember the old saying that opposites attract and likes repel, these are likes, so they're the same charge. So if you can imagine each electron being in their own little cloud blob here, then each of these cloud blobs, as they come near each other, want to move away from each other. And so they repel, if you will. And in doing so, this gives us these different shapes that we're going to go over here. So as this one, for example, tries to move towards this way, this guy here is saying, no, 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 you can't come here. So this one swings back this way. As it does, this one here puts up a point and says, no, you can't come here. And then likewise, each of these are swinging back and forth. These electron clouds are, because they've got to sort of know their boundary. You got to have the boundary limits as to how far each cloud can move. Okay? So it's because of all this boundary setting that we get the three-dimensional shapes that we get in molecules. And it's also important to remember that we're only dealing with covalent compounds, molecular compounds, nonmetal with nonmetal. We're sharing electrons. We're not giving, we're not taking, we're not doing anything with the exchange of charge. Only the sharing of electrons. Okay? So the first thing we need to be able to do in terms of Vesper is to identify how to write the Lewis structures. And so I've got some things here for you on the screen about that. That, you know, to remind you, we did Lewis dot diagrams earlier. But Lewis dot diagrams are representation of valence shell electrons. So for example, here's an atom here, and if you look at its valence ring, it has 4 electrons in the valence ring. If we, on the other hand, look at it in terms of a Lewis dot, see, the atom is carbon, there are the 4 dots there around carbon. Now you might go, well, before we did carbon like this, we said 1, 2, 3, 4. And that is true. What we've done now is what's called hybridize and hybridization. Hybridization is where we're going to move an S to become a P. And what this does is it will increase our bonding sites that we have. Notice that the one that I've drawn here in the blue, there's only 2 single dot points. That is something, 2 places where something could come in to bond to it. Okay? Something could come in here. Something could come in here. On the other hand, by simply moving one of these S's to an empty P spot, we create the black model here, in which something can come here, 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 and here. Now you may say, well, what's the big difference between these? Remember, the end goal is 8. Which carbon is going to have 8 electrons? If you look at the one in blue, it's got its pair right here, so that's 2. If it took in one here, that would be 4. Took in one here, that would be 6. In the model here in black, we've got 2, 4, 6, 8. And that's the big thing about hybridizing. So what I want you to do now for your Lewis dots is simply go around the circle twice. We're still keeping the same number of valence electrons that we did before, but we're going to go 1, 2, 3, 4. And then once we hit to 5, then we start going around the circle a second time. 5 will now pair with 1, 6 with 2, 7 with 3, 8 with 4. So go around the circle once, go around the circle twice. Okay, please don't hopscotch all around. You're not that advanced to do that yet. It's easier if you just keep it going around in the circle before anyone asks. So as some quick reminders, here are the few changes that would be made. Notice that the main changes here are those with 2, 3, and 4. 2, 3, and 4. The others basically remain the same. Notice also we still have the octet condition here for our noble gases. We also have the duet condition for helium. Remember, it's too small to have an octet. Helium, and hydrogen are the two exceptions that wish to have a duet, and so they have their duet. Helium has a duet and hydrogen wants a duet. Now, interesting thing about this particular model here, where I'm showing you two fluorines bonded together. In these two fluorines, you've got two different types of electrons being shown. At the same time, each fluorine atom thinks that they have their octet. The fluorine on the left, because it's sharing one with the fluorine on the right, thinks it has an octet, while the fluorine on the right thinks it has a octet. The difference here is this red pair that's called the bonding pair. The bonding pair, also often called the shared pair, is the pair of electrons that is shared between two atoms. It's where technically only one belongs to each atom, but they're sharing them back and forth between the two of them. If they share them equally all the time, it's nonpolar. If they share them split time, where one atom has the electrons more of the time, then that is called polar. Polar. It's more time spent around one atom than the other. But we also have these black dots here. And these black dots are the lone pair electrons. Lone, L-O-N-E. Because they belong to fluorine alone. Alone. Okay. So two big definitions that we've got here. Shared pair and lone pair. Some books will draw the shared pair as a dash. I prefer not to, because if you take AP courses, and a lot of times in college, you're not allowed to do the dashes with that. What I will do is, if I was drawing this out and only had one color, I would use dots for one element and X's for another. Now, in order to determine the Lewis structure of something, we need to know how many electrons are required. Electrons required basically are, do they follow the octet rule or not? Okay. For elements besides hydrogen, they follow the octet, meaning their electrons required are 8. Hydrogen, however, does a duet, and it needs 2. Boron requires 6. Phosphorus, 10. And you're going to see when we force some of the noble gases to bond, they will only do it if you give them 12 as a requirement. 12. These are the exceptions to the rule. And you need to know the exceptions. Hydrogen at 2, boron at 6, phosphorus at 10, noble gases at 12. Everybody else is 8 for the electrons required. That is the ER. Next up is how many valence electrons they have. To determine these, you simply look at the column that the nonmetal is in. For example, hydrogen is in column 1, so it has 1 valence electron. Chlorine is in column 7, it has 7 valence electrons. So we now have defined what a shared pair is, what a lone pair is, what the electrons required are, and what the valence electrons are. We have an equation for a shared pair. Shared pair is 1/2 the quantity electrons required minus valence electrons. Notice the placement of the parentheses. The half is on the outside. The half is on the outside of the parentheses. For the lone pair, the equation is 1/2 the valence minus the shared pair. Notice again the placement of the fraction, and you'll see there with that the fraction takes priority there so that we multiply half times the valence, and then we will subtract. In the shared pair, we subtract, then multiply. In the lone pair, we multiply, then subtract. So a couple of quick guides. We're going to determine our electrons required, our valence electrons, our shared pair, and our lone pair. And then we're going to draw this, noting that the first atom is usually the central atom, meaning the one that goes in the middle. Okay? And we put enough bonds in otherwise to satisfy our shared pair and the octet rules. Please remember, hydrogen can only form 1 bond, so it is what we call a terminal atom, meaning it is all there is. Halogens also are a terminal bond. So, let's try a couple of these. Now, for this, you're going to need, in your fill-in-the-blank notes, you have a table of that goes along with this. It's around up in the notes, a couple of pages in. It's the Vesper table. And with that, it has the names of the geometries. It has the names of the number of shared pair, number of lone pair, has the angles that go with them, has the name for the hybridization, how we move those electrons around. They all have a name just like electron configurations, these hybridizations have a name. Well, all of that you get right from reading that table, just from reading that table. So let me show you how you work out one of these bookkeeping problems here. We have CH4. This is carbon tetrahydride, by the way. How do I know that? Because there's 4 hydrogens. Hydrogen is the N, so we've got to change the ending of its name, and I don't mono the first one. So I'm going to list my elements here. I have carbon, hydrogen, 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 hydrogen. I list them all separately because I want to do the bookkeeping on each individual atom. I'm going to have my first column will be electrons required. My second column will be valence electrons. And my last line here will be my total. Now, electrons required. Let's go to our exceptions to the rule first. We said that hydrogen only requires 2, so you can fill hydrogen in for each of these. Carbon is not an exception, so that means it is 8. For the valence, we get this from the column that they're in. Carbon is in column 4, hydrogen is in 1. We now total these up, and we get a total of 16 electrons required and 8 valence electrons. Now we go to our equation. Shared pair is 1/2 of the electrons required minus the valence. So this will be 1/2 of 16 minus 8. 16 minus 8 is 8, times 1/2 is 4. There will be 4 shared pair in this molecule. Lone pair. It is 1/2 of the valence minus the shared pair. So this is 1/2 of 8 minus 4. Half of 8 is 4. Minus 4 will be 0. There will be 0 lone pair. Now to draw the Lewis structure for this, since carbon's listed first, carbon goes in the middle. We're going to give carbon its 4 valence electrons. And then I'm going to double dip here. I'm going to be both different color and use X's. I'm going to bring in hydrogen here, because I'm turning each single electron into an electron pair. Each single electron into an electron pair. So like putting a puzzle piece together. So where you have one unbonded electron, I can put a second one into it and make it into a pair. Now, if you look this up on your table, you'll see that you have 4 shared pair, 0 lone pair. You'll find that this geometry, according to the table, has the name tetrahedral. It has angles of 109.5 degrees and hybridization of sp3. 1s plus 3 p's. 1 plus 3 is 4. How many things are around the carbon? 1, 2, 3, 4. And that's how you keep up with sp3. This is carbon tetrahydride. I'm going to work another example for you. If you need to pause the video at this point and go back through it again to see this one, go ahead. But I'm going to proceed on to dihydrogen monoxide at this point. Our bottom example here is dihydrogen monoxide. Yes, it's water, but this is its scientific name, dihydrogen monoxide. So again, we're going to list down our elements. We have one O, we have two H's, we have the electrons required, and we have the valence electrons. For electrons required, again, let's do the exceptions first. Each hydrogen requires only 2, but oxygen will require 8. For valence, it's the column that they're in. Oxygen is in column number 6. Hydrogen is in column number 1. 8 and 4 is 12. 6 and 2 is 8. For shared pair, it's 1/2 of the electrons required minus the valence electrons. So this is 1/2 of 12 minus 8. 12 minus 8 is 4. Half of 4 is 2. There are 2 shared pair. Lone pair. Half the valence minus shared pair. So this is going to be 1/2 of 8 minus 2. Half of 8 is 4. 4 minus 2 will be 2 lone pair. Now, who's going to be central this time? Well, again, usually it's the first atom drawn as the center. But this time you can see we have 2 hydrogens, so how could you choose which one of those to put in the middle? So we're going to put the 1 oxygen in the middle, and I'm going to give oxygen its 6 electrons. Notice how I went around the circle twice. I'm going to now bring in my 2 hydrogens, each one of those having 1 electron each. And there is dihydrogen monoxide. Now, these red pair here belong to oxygen alone. They are lone pair. Some people like to make them into loops because that's sort of what they do physically. And so when you look at this, this is often called the Tinkerbell molecule. These are her fairy wings and these are her little feet. Some people say this is the Mickey Mouse head molecule. If you see the 2 hydrogens stuck up so like Mickey ears, whatnot with that. So either way you want to think of it. The name of the geometry, because it is nonetheless here, because we have 2 shared pair and 2 lone pair, the name of this geometry is bent angular. It also is SP3, and it is 109.5 degrees. Now this is an approximate. That's a little tilde. Why is it approximate? Because this is not part of the structure what I'm going to do right now, but these wings are flapping as they come into each other. they get repelled and they fly away and they swoop way down here and way this way, and that causes the little Tinkerbell feet to sort of kick in like it's kicking its heels. So this thing looks like it's constantly flapping its wings. So that's why it's called the butterfly molecule. Flipping and flopping and flipping and flopping. Okay. Now, this is dihydrogen monoxide. Now, I'm going to erase this, and I want to just give you very quickly the angles before we finish up this video. If you have an SP, that angle is 180 degrees. If it's SP2, it's 120. SP3 is 109.5. SP3D, then this has two sets of angles. This has horizontal angles of 120 and vertical angles of 90. And then SP3D2 has angles of 90. Now, of course, anytime you put in the lone pairs, they're going to become lone pairs, make them become approximate because they're in constant motion. If everything is a shared pair, then it's a rigid set molecule. Okay, and you'll see that more when we do these, when you make some of these in class and whatnot. Okay. All right. So anyway, be sure to look at your table in your notes. And that is everything that I know to be able to tell you right now about Vesper and Vesper theory.